Welcome back. So today we shall start lecture 29, okay, where we shall start gallium nitride RF devices. If you recall, long back or few weeks back, perhaps we had introduced the concept of polarization, 2D electron gas in an AlGaN GaN HEMT. We talked about some basic properties of the 2D electron gas in an AlGaN GaN HEMT, scattering, mobility, and the basic, how the band diagrams are drawn, the polarization charges, etc., etc. But now from in this week, where we are going to have 6 lectures from 29 to lecture 34. In these 6 lectures, okay, or 29 to 33 actually, we are, or 34 I guess, we will talk about in details about RF HEMTs of gallium nitride. We will look at how commercial RF HEMTs look like in gallium nitride, but before that we need to set the stage for really appreciating how the RF HEMTs work. In real world, what kind of RF device issues have to be addressed for making this AlGaN GaN HEMTs in practical application. Okay. So, over to the whiteboard. So, AlGaN GaN HEMT, of course we had given the very basic introduction in an earlier week. Okay. This is extremely useful for high RF power, okay, good gain, not the highest gain, but it is very good gain, and pretty good PAE, which stands for power added efficiency. These 3 qualities, and of course the linearity is not so good, I will come to that maybe later, but these 3 quantities or attributes are very important in a power amplifier. In a power amplifier, a power amplifier is the most power hungry block, is the most power hungry block in a for instance in a transmission receive module. You receive and you transmit, right, transmission receive module or a front end module maybe. The power amplifier comes in transmitting power. When you have a cell phone for instance or a base station, you want to boost the power and then send it to the nearest cell phone tower or nearest receiver, you want to boost the power and send it. So, the power amplifier has to really suck in a lot of power and amplifies the signal and send it to the antenna. So, the power amplifier is the most power hungry block or the component in an entire chain of transmitter, transmit receive module or block. So, any improvement in efficiency directly translates to improvement in the battery life of your cell phone for instance. If you can increase the efficiency, you are looking at an increased battery life, and given the fact that modern cell phone for instance or any other handheld gadgets, we are looking at so many functionalities that are being embedded together at very high data rate, very high very low latency, you want very compact, very small device, but that can do so many things, and you need to be very fast, you need the device to be very fast, agile, but you also want the battery to last very long. These are conflicting demands. If you want a smaller compact size and if you want it to be very fast and if you want to incorporate so many functionalities, it is contradictory to wanting to have a very long battery life, because you need a more power supply to have all these things. So, the RF designer today, especially the power amplifier designer, all other RF designers are at a spot. There is an increasingly stringent design constraints from the system and the users, but the material and the device can only offer so much. So, there is every bit of effort to squeeze out the maximum performance from the device or the material. Newer materials, newer device topologies are being increasingly investigated. So, AlGaN GaN HEMT fits the bill. It is not a very new technology. It has been investigated for the last 25 years or more, okay, but now things are at a commercial scale. Even for the last several years it is commercial, and it has a large market. To give you a feel, in the year 2022, the RF device market for gallium nitride was about $1.7 billion or $1.3 billion. I kind of confused, but close to $1.7 billion all over the world. Okay, was, yes, it's $1.7 billion was the RF device market in 2022. Of this, around 7.78 billion or 780 million was in the telecom sector, wireless telecom, because anytime you have communication, it is mostly wireless now. Wireless communication needs RF signals, radio frequency signals, to go and come back to receive. So, you need a power amplifier in any wireless communication. So around 0.78 billion was in telecom, I guess similar number or maybe slightly lower, slightly more number was in military for radar, radar and electronic warfare and jammer and anti-drone jammer. All these need very high power RF signals to jam a signal or to detect to use in a radar to detect an enemy warcraft or something, and the rest were other applications, satellite transponder, etc., etc. So this is a large market and it is expected to become almost double. I guess it's expected to become around $3 billion by 2028. So you are looking at a very largely expanding market of an AlGaN GaN HEMT technology. So this is the context, and this AlGaN GaN HEMT has been historically and even today primarily looked at for a power amplifier. However, more increasingly people are also looking it for low noise amplifier. Low noise amplifier, there more than power you are more worried about gain and noise figure. Noise figure is NF. Okay, gain and noise figure are very important. You are looking at low noise amplifier. That's on the receiver side. You have a low noise amplifier on the receiver side mostly, and then also people are looking at RF switch to change between one side to another side, switch between different components. And RF switch you look about things like insertion loss, for instance. People are looking at RF power amplifier in gallium nitride because gallium nitride can give you power densities that are not possible with other technologies. Okay, and when I say other technology, I mean silicon RF and I mean gallium arsenide or indium phosphide based RF. Those materials, it's impossible for them to match the power density that is provided by gallium nitride because of the superior material properties of gallium nitride. In LNA and in switch, gallium nitride may or may not have superior advantage. However, if you can make the power amplifier, the low noise amplifier and the switch in one die, we can call it a monolithically integrated circuit. You are making it in a single die, then it's an MMIC. MMIC stands for microwave monolithic integrated circuit. You can make a power amplifier also in MMIC, by the way, only power amplifier, nothing else. You can make only an LNA in an MMIC. MMIC stands for basically you have a singular die of a same material which is gallium nitride, and everything you do there, all actives, passives, via holes, transmission lines, stubs, tuning circuits, everything you have on a single die, and it's a monolithic, it's so compact. You don't have the components, you don't have to integrate components externally, it's a compact. And so many military applications, for instance, they look at MMICs, especially at higher frequencies like X band, Q band, etc. This is very, very important. But if you can also combine the power amplifier, the low noise amplifier, the switch, then this entire thing can constitute a TR module in a radar, a transmit receive module. There could be other components also, mixer, tuner, etc., etc. There could be depending on the architecture, but a TR module will be a PA LNA switch, and you can have the entire TR module on a single die, okay, MMIC die. And that is the beauty of gallium nitride, and that is why people are looking at gallium nitride to make RF switch and LNA also. And there are companies that are now starting to make these three things together and are releasing in the market, but these are very military sensitive, so you cannot import them to India mostly, and so these are of very high military importance. Okay, it's an ITAR restricted technology that you are talking about. Okay, but people are looking at LNA and switch also, although in this course we will typically look at gallium nitride device performance from the RF point of view or from the power amplifier point of view, okay, from the power amplifier point of view. And if time permits, we can also cover a little bit of LNA and switch and what they are looking at, but power amplifier is historically and even today dominant application of AlGaN GaN HEMT. Okay. So power amplifier, I told you output power, gain, power rated efficiency, okay, these are very, very important, and even linearity, by the way. Linearity is something gallium nitride has not been very good at, but now people are also looking at linearity at the device level. People used to address linearity at the systems or the circuit level by adding extra blocks, pre-distortion blocks to improve the linearity, but now people are looking at device level also. But we need to understand why gallium nitride is superior to other technologies when it comes to output power or gain or PAE. Okay. So as I told you, gallium nitride has a high band gap of 3.4 megajoule per centimeter. Say for instance gallium arsenide has this is gallium nitride. Gallium arsenide has a band gap of 1.4, silicon has a band gap of say 1.1. When the band gap is large, the breakdown field is also large. Breakdown field, the critical field of breakdown is a field at which the material will break down. It depends weakly on doping, but by and large gallium nitride has a breakdown field of around 3 megavolt per centimeter or slightly more. Silicon will have a breakdown field of 0.3 megavolt per centimeter, 10 times lower, and gallium arsenide, which probably has a slightly more than silicon. I cannot recall the exact number, but it will be much less than 3 megavolt per centimeter. It could be 0.5 or 0.6 megavolt per centimeter. Now why is it important? Why is it important? Because this means that a wider bandgap material such as gallium nitride can have higher breakdown voltage for the same dimension. For the same dimension you can have higher breakdown voltage. If you have a higher breakdown voltage, you can bias it at higher voltage, VDD, we call it VDD. VDD is the drain voltage, you can say. You can bias it at higher voltage, and a higher drain voltage bias will give you higher output power, our RF output power. Okay. So, the RF output power depends on the output voltage that you are biasing. It also depends on the maximum current that you can get, product of both, by the way, okay, the product of both. And so, if you have higher drain bias, you will get higher output power, and you can get higher, this because you can have a higher breakdown voltage. That is one part of the story. The second part of the story is that the current density also seems to be higher, because the current density depends on N. N is the charge carrier density. If you recall, the 2 DEG density of a gallium nitride HEMT, the NS is in the range of 10 to the power 13 per centimeter square. You can even get 2 into 10 to the power 13 per centimeter square, depending on the design of AlGaN GaN. This will probably give you close to 1 amp per millimeter. This will probably give you 2 amp per millimeter. These are much higher currents that you can get in other technology. For instance, the 2 DEG density in an AlGaN gas HEMT is around say 4 into 10 to the power 12 or maybe 3 into 10 to the power 12, which is also the same as in a silicon MOSFET, the kind of densities that you get. So, the current is nearly half to 1 by 3, okay, times lower. I mean it 1 by 2 to 1 by 3 times that of the current you can get in gallium nitride, and the breakdown voltage is 10 times lower in gallium arsenide or silicon as opposed to gallium nitride. What it means is that when you take the product here, correct, when you take the product here of this to quantity, the total output power can be 20 times higher than that of gallium arsenide or silicon. It can be even much more higher. You can get crazy high power. Okay. When I say crazy high power, I really mean crazy high power, but practically speaking you can say that you will still get more than 10 times. More than 10 times output power density being higher is a disruptive technology. What it means is that it will disrupt, it will replace gallium arsenide and silicon completely, as it has already started to in applications where you need higher output power at high efficiency and gain, okay, and it can become very compact and very lightweight, and it's the technology that people are looking at in all base stations, for instance cell phone base stations, in radar, military, satellite, etc. This is a fast penetrating technology and a highly military strategic technology. Okay. Now you have the higher power, you have so you have higher voltage because of higher breakdown, you have higher current because of higher charge. However, RF devices not only depend on the output power that we are talking about, only voltage or only current is not the only thing that you need to look at. You also need to look at frequency. At what frequency are you getting that? What is the speed at which you are getting that? It is very important, correct. So, if I say if I get very high voltage, I get very high current, so what? What frequency? For instance, power switches, gallium nitride power switches, power switching application is also very fast booming for electric vehicle charging. There you get 650 volt GaN devices commercially with 30 amps of current. If you have a 650 volt device at 30 amp, that is an insanely large power we are talking about, but can it go at say 10 gigahertz? Can it give RF amplification at 10 gigahertz? No. So, the frequency is also very important, correct. The frequency is also very important. You cannot increase the voltage or current by compromising on the frequency. The frequency has to be an RF frequency of the desired RF frequency, and within that constraint what is the voltage and current you can get. Okay. So, this brings me to this important figure called the Johnson figure of merit. Maybe it has been discussed in some of the basic semiconductor device courses, but very simplistically speaking, if I take a piece of semiconductor if I take a piece of semiconductor which is suppose n type doped and there is electron all about it, okay, electron all about it, and in its on state the current is flowing, and this is the length of say L, this is the length of L, correct. And when you apply, when you want to block the voltage, you fully deplete it, fully deplete this part. Suppose you can fully deplete it, which means it is devoid of carrier. When you fully deplete it, we call it a space charge region, it becomes a completely depleted region, correct. So now what is typically the breakdown voltage here? What is the breakdown voltage you are getting here? It will depend on the critical electric field, okay. The critical electric field is suppose F grid, okay. So the critical electric field is, suppose I assume it is the constant throughout the space charge region, okay. So critical electric field region times this length will give you the total breakdown voltage, but it is an overestimate because the critical electric field will not be constant, it will be a linearly decreasing slope. So it is technically not the correct, but you can say it is the breakdown voltage is roughly proportional to, or it is proportional to critical electric field into the length, okay. It is proportional to critical electric field into length. Now when you are talking about the time taken t for the electron to go from one point to another point, the edge of this, and assume that it is going at velocity of saturation, that is the maximum speed at which it can go, then your this is the length L, right. So your time taken is basically the total distance divided by velocity saturation. Actually there is a factor of 2 that will come. Why? Because it is a space charge region, it is a depleted region. So there is a factor that 2 comes because of the fact that it is a space charge region, there is a space charge transport. But anyways, you can say that tau is proportional to L by V set, correct. If you have a higher velocity of saturation, you will take less time, and of course the frequency omega, which is 2 pi f, this is your frequency omega, this is a radial frequency, this is the actual frequency. So if you look at omega tau, that is actually the it is going to be 1 because the cutoff frequency and the frequency is inversely proportional to tau, correct. Now what I am going to look at the Johnson figure of merit, if I look at these two things, then I can actually replace this L with this, okay. What I mean is that I have F critical into tau into V set equal to VBR, correct, the breakdown voltage, right. So maybe I will write it down here. So I have critical field into I have the transit time into I have velocity saturation, that is equal to the breakdown voltage. Now I can write this tau as 1 by omega, okay. So I can write this as 1 by omega, okay, and so I can take omega to the other side. So I can have F critical into velocity of saturation is equal to 2 pi f into VR, I can write it as f into VR. So the frequency times the breakdown voltage is constant, which is a material property, which is your critical electric field, which is a material property, into velocity of saturation, which is a material property. So if you have a high critical field, I told you gallium nitride has a much higher critical electric field than gallium arsenide or silicon, which are the two other dominant RF technologies. There is no other dominant commercial RF technology today, more or less. So both compared to both indium phosphide or gallium arsenide and silicon, gallium nitride has a higher critical electric field, much higher. The velocity of saturation of gallium nitride is around 2 into 10 to the power 7, which is as good as that in probably silicon or gallium arsenide, very similar. So this figure of merit is called the Johnson figure of merit, and the Johnson figure of merit of gallium nitride is higher than that of gallium arsenide or silicon. The Johnson figure of merit tells you higher the Johnson figure of merit, it means higher is your RF performance, the frequency times the breakdown voltage, which means for a given breakdown voltage or for a given drain bias, you can go to higher frequencies in gallium nitride. If you plot this, how it would look like is that if this is your breakdown voltage and this is your frequency, then it looks like something, the product of this comes like that, right. So one second. So this is your F times VBR, right. So it's something like that. if this is your silicon, it depends on the material property, correct, then this is your maybe gallium arsenide, correct, and then this is your GaN, which means for the same breakdown voltage, say 100 volt, I am actually going to get much higher cutoff frequency. This is a log plot. I am going to get much higher frequency, or for a given frequency I can go to much higher voltage in GaN, gallium nitride. So, this proves that gallium nitride fundamentally as a material is superior to other dominant technologies used in the RF electronic market, and that is why gallium nitride is very promising. Okay. And in all these cases it is the AlGaN GaN HEMT. There is an AlGaN here, there is a GaN here, and there is 2D electron gas here. Okay. You have a gate here, you have a source here, and you have a drain here. Okay. However, and I talked about the polarization in the initial few lectures, if you remember how polarization comes into picture and gives the charge. However, gallium nitride is typically grown on some substrate. Why? Because only gallium nitride substrate is very difficult to make, it is very expensive, the sizes are limited, it is not commercially viable. So, you make it on some substrate, typical substrates, but the substrate cannot be random, a piece of wood or a glass or a rubber or something. Okay, the substrate has to have a crystal structure on which gallium nitride can grow epitaxially, which means it means this crystal, the layer of gallium nitride that you are growing or depositing should be able to mimic the crystal structure of the substrate below. So, we do not have many substrates, okay, because gallium nitride has like a hexagonal structure called a Woodside structure. So, the substrate also needs to have a similar hexagonal kind of structure. So, typically there is sapphire substrate, there is silicon carbide, sapphire also is by the way Al2O3, that is sapphire, and then there is silicon 111. This is not CMOS silicon, CMOS silicon is silicon 100. These are typical 3 substrates that are used. You can also buy freestanding gallium nitride substrate, but that is more expensive, and right now there is no RF technology that is available in the market using gallium nitride freestanding substrate, it is not viable. Okay. This is the cheapest of all. Thermal conductivity of silicon is as good as gallium nitride. However, the crystal quality of the GaN that grows on silicon is not the best. So, your performance is limited. Silicon carbide has excellent thermal conductivity, the material that you grow on silicon carbide, the gallium nitride, is also excellent quality amongst all these 3, and so it is the substrate of choice for the best RF performance that you need, where cost does not matter, say military. Sapphire is also very good. In fact, sapphire is as cheap as silicon, and so the quality of GaN that you can grow on sapphire is almost as good as that you can grow on silicon carbide. Okay. But sapphire is not as much used, it has been extensively investigated as a substrate for RF devices of GaN in academic circle, in defense labs, etc., but commercially GaN on sapphire RF devices are very uncommon. That is because sapphire has a very poor thermal conductivity. Its thermal conductivity is so poor and RF devices generate a lot of heat. It is very difficult to take that heat away with such a terribly low thermal conductivity. That is why silicon carbide is the most widely used substrate to grow gallium nitride for RF, because military has been using it, space, military, and even cell phone base stations for instance, they do not care about the cost as much. They do care, but in a cell phone base station if you are going to get 10 times better performance using gallium nitride at some part of higher cost than silicon, then why not? But GaN on silicon is also now picking up. The quality of GaN on silicon is not as good, so the RF performance is not as good as that on silicon carbide, but it is still better than pure silicon, silicon LDMOS for instance. GaN on silicon can be better. So, there is a lot of research going on right now on GaN on silicon RF devices. It is all about the material quality optimization, okay, but that is what it boils down to. Okay. So, before I end the lecture, there is a last thing that I will talk to you, and which is that basically whenever you are growing on a substrate, and in RF devices almost all commercial RF devices are on silicon carbide, gallium nitride. Okay. This is gallium nitride and this is AlGaN. Of course, between AlGaN and GaN, as you probably recall, there will be most likely a thin layer of AlN maybe 2 nanometer, that helps you reduce the alloy scattering, remember alloy scattering, and also helps reduce improve the 2D density. Okay. Now, here the main problem is that gallium nitride is always UID, UID stands for unintentionally doped, unintentionally doped, which means there is a lot of background carrier. I would not say lot, but there is a reasonable quantity of background carrier. This inherent background carrier comes because of impurities that get incorporated in the crystal growth. You cannot avoid them. Impurities such as carbon, maybe oxygen, maybe some kind of silicon and other point defects, etc., etc. Also there are dislocations that come. Dislocations are missing line of atoms, they are extended defects. The extended defects. All these contribute to a background carrier concentration. What is the problem of background carrier concentration? It is mildly n-type doped, very mildly it is n-type doped. What is the problem with being mildly n-type doped? It will leak. This is a source, this is a drain. Okay. What will happen is that it will leak. This is a leakage path and you do not want that leakage path, because there is a 2d electron gas here. If the substrate, the buffer also leaks, then you are at a problem. You will have hard time pinching up the channel. Your channel will not pinch up properly, your off current will be high and you have a leakage. It is not a good device. So you want to remove this impurity, and so you do something called compensation doping. All commercially available gallium nitride wafers are compensation doped. Compensation doping means you add an impurity. You add an impurity during the crystal growth intentionally, which will suck away or which will take away these extra electrons. Okay, it's called compensating. Compensating means the background electrons that are there, these impurities will trap those electrons. Typical compensation is done using carbon atom, but again there is a range of carbon. If you do it too much, it will become n-type itself. Until a range, you can use carbon which will take away this or trap this free carrier and make the this layer highly resistive, or you can use iron, Fe. Okay. So you can use either carbon dope or you can use iron dope. Both of them introduced some kind of acceptor levels that accepts electrons from the background and makes the layer highly resistive by taking these extra electrons in them. The flip side is that because these are traps that have captured the electrons and made your layer, the buffer layer, very resistive for a good non-leaky device, the flip side is that when you do actually high power pulsing and high power actually look at performance, these traps can also release electron under certain condition, and that will lead to reliability issues. So there is always a price that has to be paid, there is always a trade-off that has to be paid, but both carbon and iron can be used to compensate the buffer in general. Okay. Carbon leads to a more deeper kind of a trap, so it makes it even more resistive and is more widely used for 650 900 volt power devices. For RF devices, mostly iron is used. Iron does not make it as resistive as carbon, but it is still very resistive and it is sufficient for an RF device, and if you add iron as an impurity, you get reasonably good resistivity without getting deep level traps, although it adds to some reliability problem most likely, but that is an ongoing research. But iron is widely used in commercial AlGaN GaN RF epitaxial stack on silicon carbide or even on silicon to that matter to make this device quality epi. Okay. So maybe with that I will end the lecture here, lecture 29. This was just about introducing gallium nitride RF devices and some of the issues in power amplifier, and why gallium nitride is used in power amplifier. We talked about the Johnson figure of merit and why gallium nitride is superior to other contemporary technologies, why it is a disruptive technology for RF, and we introduced the concept of compensation doping. In the next class, we are going to look at the device, source, drain, gate and many important things. For instance, we will talk about virtual gate and current collapse, we will talk about passivation, we will talk about gate leakage, we will talk about some of the fabrication units, etc., etc. We will start with that from lecture 30 onwards. We still have 5 more lectures in which we are going to discuss, and towards the last 1 or 2 lectures I will show you images of real GaN devices that are in the market and what does a data sheet mean. If you look at a GaN RF device data sheet from a company, how to interpret that and what to make out of that, we shall also discuss that. Okay. So thank you for your time, and I will see you in the next lecture at lecture 30.